All right, it's time to start talking about Thevenin and Norton equivalents. Basically, I'm going to give a little bit of a background for why these are important, and I'm going to show the general form of the Thevenin and Norton equivalent circuits. And then we're going to get into the general process, and then we'll go ahead and solve some examples like we've been doing. So first and foremost, I want to talk about the purpose and motivation for Thevenin and Norton equivalents, okay? So basically, actually, let me skip ahead, and then I'll come back to the... Oh, how the heck did those get there? Well, that's weird. Anyways. Oh, wow, that's got to be like a glitch. I have no idea how those got there. I am very confused. All right. Yeah, pretty weird. Let me close out of the slides and try and come back. I'm not sure what happened there. Yeah, they're gone. All right. Whatever. Anyways, so let's go here first, and I'm just going to tell you that what a Thevenin and a Norton equivalent is it's basically telling me that I can take any circuit, any set of linear elements, which in this case is voltage sources, resistors, and I can replace the entire circuit with an equivalent voltage source in series with a resistor. Now, what does that mean? Basically means if I have some resistor here, I'm going to call this my load. I'll probably have to introduce the concept of a load as well. Usually the load is what we're interested in powering. So if I'm interested in charging a cell phone, my load would actually probably be a battery. I'm going to be interested in sending current into the battery to charge it. If my load was, say, some kind of a motor that pulls current, then my current source would be my load. And so what I'm typically interested in doing with a Thevenin equivalent is I'm interested in looking at what is the voltage across my load and what is the current through my load. All right? And so what I'm saying here is I could have some crazy complicated circuit on the other, like looking into the node basically, looking into the load basically, and I can replace all that circuitry with an equivalent voltage source in series with a resistor that would give me the same V load and the same I load as the original circuit. Okay? So that is the Thevenin equivalent. It is a voltage source in series with a resistor. The Norton equivalent is the exact same principle, but it's a current source in parallel with a resistor. Okay? And then we would connect our load right here. And again, this V load and the I load would be the same with this equivalent as it would be with the original circuit. And this may be seeming ridiculous, and you might say, why in the world would we care to do that? I'm going to tell you why. So let's say you had some insane circuit, maybe not too insane, but insane enough that it would take you a really long time to solve something like this. And let's say that you are looking at your load is this resistor here that I'm going to draw in blue. And so if you wanted to solve this circuit, you would have to sit here and either do mesh analysis or superposition or one of the things that we've learned so far. And I would ask you to solve for V load and I load in this circuit. First of all, I'm never going to give you anything that looks like this, so don't worry. I'm just saying this is the motivation for Thevenin and Norton. This is why it was basically invented. It's because engineers had to look at circuits this complicated, and they do every day. Actually, circuits far more complicated than this. And before simulation software like LT Spice could just do a parametric sweep and tell me the value of the load, voltage, and current for any given assortment of these values, we had to do this by hand. And so what Thevenin and Norton does is it basically says, okay, under some conditions, I can take all of this circuitry minus my load. I can basically remove my load from the circuit, and I can determine an equivalent Thevenin circuit and an equivalent Norton circuit that would behave exactly the same way as this entire lump of elements. And then I could connect that load that I took out here, and I would get the exact same V load and I load in both cases. And that is really powerful, because that means that I can sit here now and I can maybe take out my blue load resistor. Let's say that that was a 10K resistor, and I'm interested in looking at a 20K resistor. Now, instead of having to solve this entire circuit again, all I have to do is take a simple voltage divider to determine what's the load voltage and current going to be. And then if I didn't want to, oh, my orange one's actually not what I wanted, I actually want to see how my green resistor does in there, or whatever, maybe that's a 100 kilo ohm resistor. Now again, all I have to solve is a voltage divider, and we know that that equivalent circuit is going to behave the exact same way that this circuit would, and it would give me the same load, voltage, and current. Okay, so that is the purpose of Thevenin and Norton. It is meant to replace all of the elements in a circuit with an equivalent simple circuit that can be solved very easily. And you'll notice that the Thevenin equivalent with the resistor is just a voltage divider, and the Norton equivalent with the load resistor is just a current divider. So they're very easy to solve. The hard part is determining what is this equivalent circuit, and that's what we're going to learn how to do. And we've talked about the purpose and the motivation. I've showed the general form, and so now we will go into the process for actually finding this equivalent circuit.